An analysis of the dynamic behavior of JavaScript programs by Gregor Richards, Sylvain Lebresne, Brian Berg, and Jan Vitek. This paper performs an empirical study of the dynamic behavior of a corpus of widely used JavaScript programs and analyzes how and why the dynamic features are used. This paper reports the degree of dynamism exhibited by these JavaScript programs and compares them with the accepted industry benchmark suites. 100 websites were selected from a list of most popular websites on the internet. Also, traces were recorded for the three main industry benchmark suites. Here is a list of the 17 websites that the authors believe to be representative of the full range of behaviors. Let's move on to Figure 2. Figure 2 shows the size of the programs loaded by the JavaScript interpreter in bytes. They range from small, with 280s having a source size of 116 KB, to Facebook having a size of 14 MB. The second column which says the unique source size, gives the unique lines of code. The third column, which is the trace size, gives the length of traces in events. Not surprisingly, live, which is a programming environment written in JavaScript, generates the biggest traces. Let's move on to Figure 5. Figure 5 shows an instruction mix. Here, as we can see, reads, which are green in color, and the writes, which are red in color. The reads are far more than the common writes. In the overall traces, the proportion of reads to writes is 6:1. Delete comprise only 0.1% of all events. This graph further breaks writes and deletes into various specific types. For example, prop refers to accesses using the dot notation. Hash refers to access using the indexing notation, and the INDX refers to accesses using the indexing notation with a numeric argument. Let's move on to Figure 7. Figure 7 basically stands out for the kinds of allocated objects. The Figure 7 breaks down the kinds of allocated objects at runtime into a number of categories. There are a number of frequently used built-in data types, such as dates, arrays, regexps. There are several popular benchmark suites used to determine the quality and speed of JavaScript implementations. Let's move on to Figure 17. Now, Figure 17 is also the figure of the kinds of allocated objects. However, it shows the representation of the kinds of allocated objects for all sites in comparison to the standard benchmark suites such as V8BM, SunSpider, and ROM. Figure 17 shows the kinds of allocated objects for all sites in comparison to these benchmark suites. It shows the disproportionate number of instances and arrays. We can see from the comparison that the constructed objects are overrepresented in V8BM and SunSpider. As we can see, the instances are the constructed objects, which brown in color is too high for V8BM and SunSpider, whereas DROM is almost exclusively preoccupied with arrays. As we can see, arrays, which is white in color, DROM is mostly preoccupied by those arrays. The paper concludes by giving 8 assumptions for the JavaScript enabled websites. These are the following 8 assumptions. It then goes on to show a table saying which all of these assumptions are violated by the specific websites. So this is how it shows each site which all assumptions are being present at that site. Let's move on to the second paper. The second paper is on points to analysis for JavaScript by Don Seok Jang and Kwang Mu Cho. This paper evaluates the analysis on a set of JavaScript programs and also applies the analysis to a code optimization technique to show that the analysis can be practically useful. The table 1 shows all the benchmark programs. Lines basically is the lines of code. The object creation sites reports the number of expressions which creates a new object. The third column gives the analysis time in milliseconds. The figure 6 shows the example of eliminating the redundant property references. Here on the left hand side we have the original program, and on the right hand side we have the transform program. As we can see, a.x is calculated once and it's being processed twice in the original program, whereas a.x is calculated just once and it's stored in the variable t, and the variable is used twice in the transform program. This helps for code optimization. The table 2 shows the characteristics of the original program and the program's transform by eliminating the redundant property references. PR is the number of property references and AE is for the number of assignment expressions. The conclusion from this paper suggests that such analysis can be applied to optimize the programs by eliminating the redundant property references. The results demonstrate that analysis can be practically useful.